Hello and welcome to this tutorial on convolutional neural networks. So first the outline. We will introduce CNNs or convolutional neural networks by explaining first details of its stages, which are convolution, activation and pooling, and then motivate why you should use CNNs, so what are their specific features and making them particularly attractive. These are sparse interactions, a specific way of sharing the parameters, and the learning of equivariant representations. Then we explain mathematical details of the convolution operation and continue with the implementation of a CNN with Keras to train it on handwritten digits from the MNIST dataset. Also, you will see the effect of regularization, specifically dropout. You may also have seen it already in the other tutorial on multilayer perceptrons. And finally, we open up the black box using so-called attentive response maps. So this allows us to visualize which parts of an image the CNN uses to decide the final classification. So what is a CNN doing in detail? So first you start with a pixel image, image represented by pixels, like this panda, and then you apply convolution. So you have a filter 2 by 2 here with values filter with weights W, X, Y, and Z, and you slide that filter across the whole image. So in the first step, you have this overlap here as indicated by the blue area. You multiply the values of the overlapping pixels, A times W, B times X, and so on, and you sum up the result. Then you slide one, slide one pixel to the right, and then multiply B times W, C times X, and so on, and sum up the result. This gives you, after you have scanned through the whole image, you get a new feature map. And what is very important is that these weights here, W, X, Y, and Z, are learned during training. So the CNN adapts to the data and extracts specific features. So for example, lines or specific facial features in the panda face. And then you can also apply several filters and obtain a stack of feature maps. What this gives you is equivariance, not invariance, but equivariance with respect to translation. So that means if the panda moves in the image left to right or so, then the output of the filters will move accordingly. So in an equivariant way. And then you apply activation functions. Typically you use the ReLU, the rectified linear unit, which you also may have seen already in the multilayer perceptron tutorial. And this activation function is very commonly used and basically cuts off the negative part. After that, subsampling is typically applied. It's also optional in principle. And the most common method is max pooling, where you can divide the image into also maybe in principle rectangular regions, but here it is quadratic. And in each quadratic region, the maximum value is selected. So here it is 30, 11, 20, and 13. And this way you can reduce the number of features. This, on the one hand, controls overfitting, and on the other hand, you also get local translational invariance. So now really invariance, not equivariance, because you can imagine if you have, for example, the position of the eyes in the image vary a little bit by a couple of pixels due to noise in the camera, for instance, then if this local translation falls into these areas where we average over, this will not matter. This will not influence the final result. In particular, you can repeat these convolution and max pooling layers as often as you want, and at the end you want to do a classification here. You want to say, is this a panda or something else? And for that one typically uses a multilayer perceptron. So a material science application is work done in our group here, where a given atomic structure is represented via a diffraction fingerprint. This is essentially an image, so we can directly apply these techniques here. And then the crystal structure classification is performed using a convolutional neural network, of course, at the end, again, a multilayer perceptron. So thank you very much for your attention. You can contact me during the tutorial or otherwise later via mail. Thank you very much.